In the name of Almighty God, I'm Mahsa Sankasha, and today I want to talk about acoustic horn, nonlinear sound propagation using the Westervelt model. An acoustic horn is a tapered sound guide that provides an impedance match between a sound source and the air to maximize sound transfer efficiency. It works by channeling sound from a narrow throat to a wide mouth, improving how sound waves are transferred to the atmosphere and often directing them in a specific direction. This principle is used in various applications such as musical instruments, for example, trumpet, public addresses systems, and even some older phonographs. And how it works: acoustic impedance matching. A horn acts as an acoustic transformer by matching the impedance of the sound source, like a speaker diaphragm, to the impedance of the air. This is crucial because a large difference in density between the source and the air leads to inefficient sound transfer without a horn. The next is tapering. The horn's cross section gradually increases from the narrow throat to the wide mouth. This tapering guides the sound waves in and increases their amplitude as they expand into the larger opening. The next one is directivity. The shape of the horn can also control the direction of the sound, focusing it into a specific area. The next one is passive component. A horn doesn't amplify sound in the way an electronic amplifier does. It is a passive component that improves the efficiency of sound coupling to the air. And what are the applications? The first one is musical instruments. The shape of instruments like trumpets and tubas is a form of acoustic horn. The next one is pro audio and hi-fi. Horn-loaded speakers are used in professional audio and high-end hi-fi systems for their efficiency and controlled directivity. The next one is phonographs. Early record players use a horn to funnel the sound from the stylus vibrations to the listening room. The next one is ultrasonic horns. In our industrial applications, ultrasonic horns use a similar principle to concentrate ultrasonic energy for processes like welding, cleaning, and homogenization in liquids and solids. The next one is megaphones. A megaphone is a simple portable acoustic horn designed to amplify and direct a person's voice. And what about nonlinear acoustics, or NLA? Is a branch of physics and acoustics dealing with sound waves of sufficiently large amplitude. Large amplitudes requires using full systems of governing equations of fluid dynamics for sound waves in liquids and gases, and electricity for sound waves in solids. The equations are generally nonlinear and their traditional linearization is no longer possible. The solutions of these equations show that due to the effect of nonlinearity, sound waves are being distorted as they travel. A sound wave propagates through a material as a localized pressure change. Increasing the pressure of a gas or fluid increases its local temperature. The local speed of sound in a compressible material increases with temperature. As a result, the wave travels faster using the high pressure phase of the oscillation than during the lower pressure phase. This affects the wave's frequency structure. For example, in an initially plain sinusoidal wave of a single frequency, the peaks of the wave travel faster than the troughs, and the pulse becomes cumulatively more like a sawtooth wave. In other words, the wave distorts itself. In doing so, other frequency components are introduced, which can be described by the Fourier series. This phenomenon is characteristic of a nonlinear system since a linear acoustic system responds only to the driving frequency. This always happens, but the effects of the geometric spreading and of absorption usually overcome the self distortion, so linear behavior usually prevails, and nonlinear acoustic propagation happens only for very large amplitudes and only near the source. Additionally, waves of different amplitudes will generate different pressure gradients, contributing to the nonlinear effect. And what about physical analysis? The pressure change within a medium causes the wave energy to transfer to higher harmonics. Since the attenuation generally increases with frequency, a counter-effect exists that changes the nature of the nonlinear effect over distance. To describe their level of nonlinearity, materials can be given a nonlinearity parameter. The values of and are the coefficients of the first and second order terms of the Taylor series expansion of the equation relating the material's pressure to its density. The Taylor series has more terms and hence more coefficients, but they are seldom used. Typically, values for the nonlinearity parameter in, in biological mediums are shown in the following uh, table. For example, the material for blood, it is 6.1, brain it's 6.6, fat is 10, liver is 6.8, muscles is 7.4, water is 5.2, and monatomic gas is 0.67. In a liquid, usually a modified coefficient is used as now. And what common occurrences sonic boom. The nonlinear behavior of the atmosphere leads to change of the wave shapes in a sonic boom. Generally, this makes the boom more sharp or sudden as the high amplitude peak moves to the wavefront. And what is acoustic levitation? Acoustic levitation would not be possible without nonlinear acoustic phenomena. The nonlinear effects are particularly evident due to the high-powered acoustic waves involved. Ultrasonic waves, because of their relativity high amplitude to a wavelength ratio, ultrasonic waves commonly display nonlinear propagation behavior. For example, nonlinear acoustics is a field of interest for medical ultrasonography because it can be exploited to produce better image quality. And what about musical acoustics? The physical behavior of musical acoustics is mainly nonlinear. Attempts are made to model their sound generation from physical modeling synthesis, emulating their sound from measurements of their nonlinearity. The next one is parametric arrays. A parametric array is a nonlinear transduction mechanism that generates narrow, nearly side lobe-free beams of low-frequency sound through the mixing and interaction of high-frequency sound waves. Applications are, for example, in underwater acoustics and audio. And what about a Westervelt equation for acoustic wave propagation through weakly stratified arbitrary Mach number atmospheres? A Westervelt equation for weakly stratified arbitrary Mach number atmospheres has been developed to model nonlinear sound wave propagation, especially infrasound over long distances. This equation, derived from a second-order nonlinear wave analysis, accounts for both cumulative and local nonlinear effects in a moving atmosphere and is more accurate than previous models limited by low Mach number assumptions or being numerically intensive. The derivation considers acoustic effects in a moving atmosphere and can be used with numerical methods for a more realistic representation of atmospheric nonlinearities. And what are the key features? The first one is target application. Accurately models nonlinear distortion of sound waves such as infrasound in realistic atmospheric conditions, including of the uh, thermospheric altitudes. And the next is accuracy, provides a more precise and computationally efficient alternative to high fidelity Navier Stokes simulations for this type of problem. The next one is physical conditions, specifically derived for atmospheres that are weakly stratified and can have an arbitrary Mach number. And the next one is nonlinearity, incorporates both the cumulative nonlinear effects characteristics of the Westervelt equation and the local nonlinear effects that are significant in the near field. The next one is a derivation. It is a nonlinear wave equation that builds upon previous work by including the effects of a moving stratified atmosphere and how it improves upon existing models. The first one is overcoming limitations. The new equation overcomes limitations of previous models, which were often restricted to low Mach numbers or weak computationally expensive. The next one is Westervelt equation with atmospheric effect. It is an extension of the classical Westervelt equation, a model that describes cumulative nonlinear effects in a fluid medium. By incorporating the effects of the atmosphere's motion and stratification. And what about realism? It provides a more realistic model for sound propagation in the atmosphere compared to the models that assume a static medium or a constant Mach number. Metamaterials have emerged as a focal point in the contemporary science and technology due to their ability to drive significant innovation. These engineered materials are specifically designed to cope the phenomena of the different physical natures, thereby influencing processes through the mechanical or thermal effects. While much of the much dominant recent research has concentrated on frequency conversion into electromagnetic waves. The field of acoustic frequency conversion still faces considerable technical challenge. To overcome these hurdles, researchers are developing metamaterials with customized acoustic properties. A key equation for modeling nonlinear acoustic wave phenomena is the dissipative Westervelt equation. This study investigates analytical solution using anastas-based methods combined with light symmetries. The approach presented here provides a versatile framework that is applicable to a wide range of fields in a mathematical design. This simulation shows how to include local nonlinear effects when simulating the acoustic of an exponential horn. Nonlinear effects become important when an acoustic horn is used for high amplitude signaling. The nonlinear acoustic or Westervelt contributions, a feature available for the pressure acoustic transient interface, provides nonlinear contribution to the linear acoustic wave equation. The model also includes the exterior field calculation feature, which accompanied by the time to frequency or uh, fast Fourier transform study step, make it possible to visualize the radiation pattern of the acoustic field at any given distance from the source. And here we can see the nonlinear or Westervelt sinusoidal wave. And here I have used for acoustic horn nonlinear the pressure acoustic frequency domain and pressure acoustic transient. There are two different physical measures, and you can see the plot. This is a contour plot for acoustic pressure. You can see the narrow throat for the mass. And this is acoustic pressure for normalized to density, sound pressure based on decibel, nonlinear acoustic pressure, and linear acoustic pressure pressure at point plot, normalized pressure at points, and the last is fast Fourier transform operation at point. Thank you so much for watching my simulation until the end. Here you can download this simulation from github.com/acoustic horn nonlinear.